for inviting me to give a talk, and thanks Simon for nice introduction and also giving me high pressure. Okay, so let's start. So I'm going to talk about something. I'm going to talk something about large charge and holography, and the theme of the talk is large charge and holography. And today I in particular focus on U and n equals 4 super mill theory. And a kind of questions that I'm going to discuss in my talk is, for example, what's the counterpart of the large charge EFT in holography? Or what is the large charge sector? Yeah, how do you describe it in higher rank n equals 4 super mills? And of course, like there was a very nice talk already by Philip in this workshop, and hopefully I can give some complementary viewpoint. Okay, so this is the plan. So it consists of 3 parts. The first part is about large charge in n equals 4 super mills, especially with U and gauge group. And this is based on the work that will appear soon with Clay Cordova and Fran Coronado, Costa Zarembo, and Victor, Nikita, Slava, and Kolya. But those are not, for example, Nikita and Slava that you know. Those are amazing undergraduate students in Moscow. And who basically did all the main computations. In the second part, I'm going to talk about double scaling limit and a center extension, which is work in progress with Joel Caetano, who used to be in Simon Center and is now moving to CERN, and Yifeng Wan, who was in Harvard and moving to NYU. Okay, so in the third part, I'm going to talk about large charge expansion on the Wilson line defect CFT, which is again based on the work that will appear soon with Simone Giombi and his student Ben Dugatz-Over-Taylor. Okay, so large charge expansion in n equals 4 super mills. So before I begin, let me just say a few words or give a review of the large charge expansion in generic conformal field theory. So one of the main or like a fundamental prediction from the large charge expansion of conformal field theory is that if you consider conformal field theory with U1 charge and then ask a question of what is the minimal dimension of the operator for a given charge J when J is very large, then the large charge expansion basically gives you a prediction of the leading power, which is J to D over D minus 1 for a D-dimensional CFT. And this is basically coming from a simple and intuitive dimensional analysis. So in order to understand it, you consider CFT on R times ST minus 1, where RT is the time, and put the theory on a sphere ST minus 1 with radius R. Then if you quantize the theory, then the energy of the state, because of the state operator correspondence, is related to the dimension of the operator. But in order to match the dimension, you need to put 1 of R here. And on the other hand, the charge of the state on ST minus 1 is just given by J, which is the same as the charge of the operator. And now the crucial assumption is that you assume that this large charge state, which corresponds to large charge operator, becomes in the R infinity limit in which like a sphere decompactifies. You assume that it becomes a state on a flat space with finite energy and charge densities. And if you assume it, then automatically it tells you that energy should scale like epsilon times RD minus 1, where epsilon is some finite number, whereas charge is given by J times RD minus 1, where J is again finite number. And if you combine these two equations, then you can immediately see that delta should scale like J to D over D minus 1. And this minus 1 basically comes from this extra R dependence. And as you can see, that this argument is quite robust because it just relies on this behavior, and you can actually get the same scaling in a kind of like a more very different setup, which is basically ADS CFT setup in which you analyze ADS RN black hole. And that was discussed in this nice paper. Okay. So, however, we should keep in mind that this is a prediction for generic CFT, but not to all, it doesn't apply to all the CFTs, because if you consider superconformal field theory, then this prediction is actually wrong, because we know that in superconformal field theory, there are BPA states whose dimensions scale linearly as charge, and which is much smaller than J d over d minus 1. And this is basically because if you take BPS states and then take the same large R limit, large radius limit, then it actually becomes a state in a flat space with zero energy, but non-zero charge density. And this is related to the fact that these SUSY theory have flat direction, and you can actually break the symmetry by giving a wave to a scalar field. Or more concretely, you can approximate the large charge state by considering some linear combination of the flat space state with a broken vacuum, where this vacuum theta means that you are giving a wave to a complex scalar field in the direction specified by this angle theta. And this was very much worked out in detail for rank 1 theory in n equals rank 1 n equals 2 superconformal field theory in 4 dimensions, in which there is a one-dimensional vacuum manifold. And there, in this paper, they show that a large charge expansion can be basically obtained by the Coulomb branch effective field theory. And this Coulomb branch effective field theory gives you a prediction for the two-point function of the Coulomb branch operators. And this you can actually verify using the localization. So let me just make several side comments. So as I said, so in SUSY theory, you have a dimension which scale linear in charge. And because this is much, much smaller than a generic CFT behavior, if you have this kind of operator for J very large, then this almost automatically implies that there should be some vacuum manifold. However, what is more non-trivial is to show the other way. So, for example, you can ask whether you can show that if the SUSY, if your conformal field theory on flat space has a vacuum manifold, can you show that the dimension of the operator scales linearly in J? And if you can show it, then it actually is kind of interesting, because if the dimension of the operator is linear in large J, then if you further combine it with, say, convexity conjecture discussed by Aaron Pauti in this workshop, then it basically says that combining these two, it suggests that the dimension of the operator should be really linear, even for finite J. But at this moment, we don't have a proof, like an argument or proof for this direction. However, I should also say that in all the known examples that this is correct. And one thing I wanted to mention is that a similar statement was actually made in the condensed matter literature and in this paper, Saki and Watanabe. I guess Watanabe gave a talk, but probably on a different subject in this workshop. So there, they show the relation between what they call vanishing charge gap and the existence of diagonal long range order. And basically, this vanishing charge gap translates the linear spectrum, whereas the existence of the vacuum manifold basically translates to the off-diagonal long range order. So this was just a side comment. So now, yes.
May I ask a question?
Sure.
Yeah, sorry. Can you be a bit more specific on why you think it is trivial, the first point?
Okay.
I would have thought the other way around, that the second point was actually easier than the first one.
Right. So if the scaling, if the dimension scale much smaller than what you expect for the generic CFT, then if you take a decompactification limit, then the energy density basically becomes 0. Because in order to have a finite energy density, you do need this scaling. But it doesn't tell you that it's comes with 1. It can be anything smaller than this.
You're saying just because you have a non-trivial macroscopic limit,
Right.
which
Right.
is with zero energy density. Okay.
Right, right.
Okay, thank you. Sorry.
Yeah, thanks for asking the question. And please interrupt me. So, okay, so now let's talk about higher rank. So this was really just a side comment. So I'm going to talk about the main thing, which is what I'm going to discuss. And well, for the higher rank, not much has been explored. And there is a reason why not much has been explored, because there are several difficulties. And the first difficulty is that if you consider higher rank series, then there is actually multi-dimensional vacuum manifold. And depending on where you are, there is a variety of Higgsing pattern. For example, if you consider SU2n equals 4 supermills, then there is like only one Higgsing pattern going down to U1s. But if you consider SUN, then there can be like various different Higgsing patterns. And another difficulty is that the classification of supersymmetric higher derivative terms become complicated in the higher rank theory, but there was progress reported by a talk by Philip. And there is also a third point, which is the degeneracy of the BPS operator. So in the SU2 theory, there is basically only one large charge operator, which for each given charge. But for SUN, you can actually write several different expressions, and all of which can serve as a large charge operator. And the fourth point is more technical. And if you want to get the result from a localization, like some prediction for the 2-point function of like a Coulomb branch operators from localization, and then the computation gets more complicated. I'm going to mention a little bit in the third part of my talk. So now let's discuss the point 1 and 3 and in some simple toy model and see how they are related. So this is a toy model that I'm going to discuss, which is like a simplest toy model. So it's actually zero-dimensional complex matrix model where Z and Z bar are n times n complex matrices. So let's now consider, furthermore, I considered some Gaussian complex matrix model and considered a 2-point function, O and O bar. And where O is made out of Z and O bar is conjugate. So it's made out of Z bar. And using the result by Ginipre, you can actually rewrite this in terms of eigenvalue integrals. So this is in some sense like a complex matrix version of the usual Hermitian matrix model. And the result is given by this expression. So the small zi's are basically the eigenvalues. Now let's take a single trace operator. Let's first take a single trace operator, O equals trace Z to J, and then insert it in this path integral. So then each single trace operator is given by like a zk to j summed over k. And because we also have O bar, we can have like a 2 integrals. However, using U1 invariance, you can show that only like diagonal term survives. So you get expression which is like a sum over k z to the power k to 2j. And furthermore, if you use the permutation invariance, then you can actually rewrite, because like all the other terms are permutation invariant. So you can just replace this with n times z1 to the power 2j. And this expression clearly tells you that there is a source term only for z1. And which means that this original un symmetry gets broken because of this extra insertion to u1 times un minus 1. Okay, so let's consider slightly different operator, which is a double trace operator. So naive expectation is that because a single trace operator corresponding to u1 times un minus 1, maybe the double trace operator corresponds to u1 times un minus 2. But that's actually, precisely speaking, not correct, because if you follow the same argument, then you get this kind of expression. In NMM, each NMM corresponds to like each single trace operator. And this sum, double sum, can be decomposed into the following way. So the off-diagonal terms plus diagonal term. And the point is that off-diagonal term does give you the symmetry breaking pattern you expect, but there is a diagonal term in which the symmetry breaking pattern is just given by u1 times un minus 1. So this means that if you just take the double trace operator, it gives you a mixture of the Higgsing pattern. So the correct operator, which corresponds to this Higgsing pattern, is to take the linear combination and basically subtract this part.
Can I ask you a question?
Sure.
Is there a way in which the single trace operator, multiple trace operator have a different n scaling so that taking some limit like large n separates them or something?
Okay, okay. Right, so I see. So you are
I don't know. I was just wondering.
Yeah. Well, well, probably here you do need two terms, even in the larger limit, I think.
Right. I mean, the fact that you write that one makes me think that the answer to my question is no. But I was wondering how obvious it was.
Right. Yeah. I don't have any sharp answer. Yeah. So this one indeed does seem like you need both terms. But okay, so let me just continue. So it can be generalized to other Higgsing pattern, and which is, well, for this matrix model is kind of straightforward yet tedious. Of course, like the matrix model that I talked about is not n equals 4 supermills, but the toy model captures kind of like essential features of n equals 4 supermills. And if you really want something very concrete in n equals 4 supermills, you can actually just like look at the 3-point function of half BPS operator, where two of the operators are like a large charge operator, and the third operator is some like a light single trace operator. And thanks to the n equals 4 super symmetry, this 3-point function is treatable exact. So you can just like compute it using the weak contraction. On the other hand, the 1-point function of this operator, this kind of operator on the Coulomb branch is also treatable exact. Well, as long as you give a web to only one scalar. So basically, you can compute both sides and then figure out what kind of Coulomb branch or Higgsing pattern corresponds to what kind of like a large charge operator. So this is something you can explicitly do, even at finite n. And so this allows you to establish a dictionary between the large charge half BPS operators and Higgsing pattern. And in particular, if you consider U1 times UN minus 1, then indeed you can check that it's given by a single trace operator, as in the case of a large matrix model, toy model. And one can even write a very, very concrete formula, which extends to non-BPS operators. So this is the formula for U1 times UN minus 1. So let me just show you formula, which is this one. So the left-hand side is defined in the conformal, at the conformal point. So this is just like a large charge correlation function. And this O1 to On can be anything, although like at this moment, it is still just a conjecture. Whereas on the right-hand side, you have a correlation function of the same operators on the Coulomb branch. And the left-hand side, what you need to do is to like put several operators near the origin, and then put two heavy operators far from those operators, and the direction is given by n, and the distance is given by r. And then you integrate over this direction. So basically like integrate over the sphere, and then take a limit in which the charge becomes infinite and also the distance becomes infinite, whereas this combination is held fixed. And on the right-hand side, there is some integral. And let me just explain what this is. So this Coulomb theta means that you are giving a vev to a particular direction of the scalar. So in n equals 4 supermills have 6 scalars, and I'm giving a vev to the first 2 scalars, and relative magnitude is specified by theta. And because I'm talking about U1 times UN minus 1, I'm giving a vev only to one component. And this relation is verified, and actually it was derived by analyzing the 3-point function of BPS operator. So like I just replaced this with one light BPS operator. And you can in principle also check it for higher point function by looking at the chiral algebra sector. And furthermore, in principle, like it can be generalized to other Higgsing pattern. But the most important point is that, well, this is still a conjecture, but the conjecture is that this relation is valid also for non-BPS operators. And this is actually very nice because in the large N limit, this is still work in progress, but there is evidence that you can actually compute right-hand side using integrability, whereas the left-hand side is not computable because like you are taking charge to be very, very large. So this allows you, if this relation is really true for non-BPS operators, then this allows you to give some limiting behavior of this quantity using, allows you to compute this limiting behavior from the integrability analysis. Okay, so let me now briefly mention the holographic description of this object. So in n equals 4 CPMLs, if you take a planar limit to fifth limit, this trace z to j with large j, in particular when j is of order n, is dual to what's called dual giant graviton, which is basically spherical D3 brane living inside ADS5. And the size of the brane is given by j divided by n, which I denote by small j. And now, if you take the limit in which this small j goes to infinity, then D brane basically approaches the ADS boundary. And although initially it was a spherical brane, and if it approaches the boundary, you can actually approximate it by a flat D3 brane. And this is the flat D3 brane, which describes the n equals 4 CPMLs on the Coulomb branch. So in this sense, like this holographic description gives you a geometric realization or a geometric explanation of why the large charge expansion works and why the large charge expansion is related to the Coulomb branch. And in this context, the dBi action plays the role of the large charge EFT. Okay, so this was the end of the first part of the talk. But let me just pause here and before going to the second topic.
Can I ask you a question?
Sure.
It's about this thing that the dBi action is the same. Well, it should be the same thing as the large charge EFT. Can one use that to figure out what are the higher order terms that appear? In the sense, just because dBi action is an infinite expansion, and
right.
Yeah. Now we spoke about one term, but
yes. I guess probably dBi action. Of course, like we don't. Yeah, dBi action should capture some parts of the large GFT, but I don't have much more intelligent.
No. I totally like that sentence you said. That I was just thinking if you can do something.
But I don't know. Maybe Simeon has some comments because he turned on the camera.
Yeah, but he's not turned on the microphone.
I was going to say maybe the leading large n pieces in the regime with J and N scaling the same way. That's what it sounds like.
Yeah.
Okay, thank you anyway.
Yeah.
So I have another short question. I mean, so what you said suggests that you should be able to generalize this also to multi-trace operator and to multiple three branes on the Coulomb branch. I mean, so I guess you're investigating that as well, or I mean, or is there some obstruction to that?
Well, if you have a multiple, if you consider multi-trace, then like you basically get like a concentric, several concentric D3 branes.
Yeah. So there should be similar formulas to the one you wrote, to the conjectured formula you wrote also in that piece. Okay, good. Thanks.
Right. Okay, so let's now move on to the second topic, which is probably short. So this is the topic that I'm working with Joe Caetano and Econ 1. So now I'm back to rank 1 series, but still in n equals 4 CPMLs. So by which I mean I'm talking about SU2 n equals 4 CPMLs. And so to motivate it, let me just remind you that the large charge expansion of superconformal field theory receives exponentially small corrections. So in addition to these 1/j corrections, that you can determine using the large charge EFT, there is also exponentially small corrections. And those exponentially small corrections come from massive BPS particles in flat space. So it cannot be, it's not like a directly incorporated into the action of like a low energy EFT on the Coulomb branch, but it's rather like a massive BPS particle. And the reason why massive BPS particle gives you this is that like if you just carefully like if you write this expression and then like carefully translate what the mass is in terms of J, then you indeed discover that you get minus GMS times square root of J. And interestingly, these authors proposed a kind of interesting limit in which this kind of like a exponential corrections get enhanced. So which is called a double scaling limit by now, which is to take J to infinity, but keeping GMUs times square root of J to be fixed. So if you take this limit, then it's obvious that this exponential correction survives because it's order 1. So this is a little bit like a 2-fifth limit, but we need to remember that we are only talking about SU2 series. So it's kind of like a 2-fifth limit defined using the charge. Now, so as I said, like these corrections come from the massive BPS states in flat space, and it is well known that the massive BPS states in flat space are basically short multiplet of the centrally extended Poincare-Suzy. For example, like you have QQ commutative momentum, but in the case of central extension, you can put some central charge on the right-hand side of the Q commutator, anti-commutator of Q and Q. And those short multiplet basically satisfy BPS bound in which mass is equal to absolute value of J. And this use of the flat space Suzy is justified in the usual large charge limit, because in the usual large charge limit, if you estimate the Compton wavelengths of the BPS particle, then it's given by, again, like 1 over GMUs times square root of J, which is very small if you keep GMUs fixed and take J to be large. So therefore, like you can neglect the curvature of sphere, and then you can just use a flat space Poincare-Suzy. However, this argument, precisely speaking, doesn't work in the double scaling limit, because if you estimate the mass of BPS particle in the double scaling limit, it's again given by this combination, and this combination is order 1. So basically the particle knows about the curvature of the sphere. So then you can ask, what is the symmetry governing this double scaling limit? And here is an answer. The claim is that the relevant symmetry, at least, well, for n equals 4 supermills, is again centrally extended symmetry, but it's not a centrally extended Poincare symmetry, but it's a centrally extended SU2/2 square symmetry. So here you have supercharge, and here you have like a superconformal charge, and there are 3 central charges that you can write here. And this symmetry is actually exactly the same symmetry as was discussed by Weisert and other peoples to solve large n equals 4 supermills, in which n is infinite and GML square times n is fixed. And here we are in a completely different limit, but we are claiming that the same symmetry actually plays a role. And so let me now give you why we think this is true. So there is a very simple kind of like a derivation for the case of SU2. So to derive this, we just need to remember the Suzy transformation rule. So if you take supercharge to the boson and act it to the boson, you get fermion, and that's what supersymmetry tells you. And if you take supercharge and act it to the fermion, then you have several terms typically, but in particular, you get this commutator term if you are thinking about gauge theory. And this basically means that if you consider Q square, Q square, and then take act it to the boson. So this Q square means like you take like 2 different supercharge and act it to the boson, act them to the boson, then you get this kind of term. And in the large charge limit, in the presence of like other heavy operators, and the large charge operator basically creates some like a vacuum, the profile of the scalar field, and which is like in the case of SU2V and V0 0 minus V. And because of this, like if you consider like an off diagonal part of this boson field, then this boson field gets multiplied by two times V if you take a commutator. So this basically gives you an explanation why that Q anti-commutator of Q and Q is non-zero, and it's given by some GM Mills times V, where V is basically like a vacuum expectation value sourced by the large charge operator. And furthermore, on R, if you consider like RT times S3, then Q, the Hermitian conjugate of Q is superconformal. And the algebraic consistency requires that, like, if you have this, then you should also have like this central charge for the anti-commutator of S and S. And if you then complete the algebra, then you can actually derive the centrally extended SU2/2 square symmetry. And then, okay, so it's
a very quick question. I'm sorry.
Yes, no problem.
It was just about dimensional analysis. I thought, I mean, Q has scaling dimension 1/2 and S has scaling dimension -1/2.
Right.
So then how do S and S close on V? Because V is scaling dimension 1, right?
Right. So let me.
Oh, sorry. No, well, you have Q dagger equals S. There's probably some factor of the radius in there. Is that?
Yeah. I think like I'm omitting like a radius like everywhere. So
I understand. Yeah, sorry about that. I understand.
Yeah, so in particular here, like I'm setting radius to be 1. So
okay, can I ask you a more naive question? Is this the equivalent of the superalgebra on flat space, but on R cross S3? I mean, is it like doing? Is it literally that, like doing the curved version of n equals 4?
Curved version of...
You see, instead of defining here, you must see the radius of the sphere. So naively, I would have imagined I really need to keep track of the fact of the geometry as a sphere. So I was wondering if this was just I mean, my first attempt would have been to try to generalize the algebra in flat space to this geometry here. I was wondering if that's what you get.
You mean like well,
like supersymmetry.
Yeah,
that's what I was.
Yeah. Well, in some sense, yes, but I guess in some sense, like algebra is bigger because like we are using superconformal symmetry. Sure. Yeah. Of course, like you can also like try to put some massive quantum supersymmetric quantum field theory on a sphere. But those theories have less symmetry because like you are not starting with the superconformal theory.
Okay, no, I will just, okay, thank you.
Can I think of this algebra as the subalgebra of the conformal algebra that preserves the operator insertions? Or
yes, so right. So without central extension, yes. So the SU2/2 square is precisely that. It's the subalgebra of the superconformal algebra, which preserves like two heavy operators. Okay, so one can now ask like whether this relation is anyway useful, and well, I would claim that it's useful to some extent. And for example, you can try to ask like what are the spectrum of massive excitations above the large charge vacuum, and which typically correspond to some kind of non-BPS state, which is obtained by like adding some quanta to the large charge BPS operator. And you can say from this symmetry argument that one should be able to classify them using this, well, short representation of the centrally extended SU2/2 square symmetry. And this allows you to classify the excitations. And in addition, because the algebra here is so constraining, you can actually determine the dependence on this like a large charge to foot coupling. For example, the energy of this excitation well, in some simple case, like an energy of this excitation is given by, well, if you do the perturbation, then you discover that these numbers. But then like it actually like nicely combines into this nice square root. And this like a recombination is basically explained by the existence of the algebra. And furthermore, one can hope that one of the J corrections, which come from like a interaction of those excitation, should be determined by SU2/2 invariant S matrix, which was analyzed by Bizet. But this part is still work in progress. Okay, so let me just end with several comments. The first comment here is that large charge expansion, well, relates the centrally extended Poincare SUSY and SU2/2 square. And what's interesting is that this Poincare SUSY is in a sense like a particle, like a SUSY that determines particle, but this SU2/2 square is the symmetry that determines the operator. So in some sense, like SU2/2 is a S3 version of the Poincare SUSY. And this kind of interesting relation is a bit similar in spirit to this work, in which they found some relation between the BPS particle index and superconformal index. But there are, of course, like the details of the setup is quite different. For example, like we are in the large charge regime and we are discussing non-BPS operators. And another comment here is that a similar story should exist for n equals 2 superconformal field theory, in which case one expects a single SU2/2. Okay, so this was the end of the second part. Let me pause again to see if there is any question.
So can you analyze this also at higher rank, or does it become too complicated?
In principle, the symmetry should be there in higher rank, but I think like one can try to work it out, and it's not too complicated, but it's certainly more complicated than SU2. Okay, so now moving on to the third topic, which is the large charge expansion on the Wilson line defect CFT. So here I am mainly going to talk about holography and defect CFT. So to introduce the third part, let me just remind you yet another beautiful story about the large charge expansion, which was done in this paper in 2019. So what they did is to analyze the extremal correlators in rank 1 n equals 2 superconformal field series. And in particular, they analyzed this 2-point function of the large charge operators. And they basically, and these 2-point functions are computable from localization of deformed S4 partition function, which I denote by Z of S4. And more concretely, you can actually compute this. The final answer for this is given by some determinant. So here you have S4 partition function, and these tau and tau bar are coupling constants. And you construct the matrix like this, and then take a determinant. And for rank 1 theory, this partition function on S4 is just given by a single integral. And the basic reason why you need to take determinant is because if you consider operators on S4 and try to relate it to the operator on R4, there is a non-trivial mixing, and then you need to do kind of Gram-Schmidt orthogonalization in order to get the operator on R4 from the computation on S4. And the Gram-Schmidt orthogonalization gives you this determinant. And an interesting observation made by these authors is that this determinant can be reformulated into matrix integral. And the size of the matrix is actually given by J times J, where J is the size of the charge. And this is very interesting because in this reformulation, 1 over J expansion, namely the large charge expansion, corresponds to the genus expansion or topological recursion in this like an emergent matrix integral, or the spectral curve that you obtain in the large J limit. And again, so here they did the computation for rank 1. And again, the generalization to higher rank is complicated, partly because of the degeneracy of operators. And however, remarkably, things actually simplify again if you take the large n limit. And that's basically because of large n factorization. So in the large n limit, you can kind of cleanly separate single trace operator and double trace operator, and that allows you to do the computation to do the Gram-Schmidt computation. And the final answer is roughly given by this. So very roughly, in the rank 1 theory, I wrote this formula, which is given by the derivative of the sphere partition function. But in the case of large n, you basically just need to replace this z by F0, where F0 is basically the genus 0 free energy. So you basically take a log of z and then keep the term which is leading in large n expansion. So that, roughly speaking, gives you the correct answer for the large n formula, and basically similar observation was made in this paper. And this is actually nice because even for the large n, because like the structure of the answer is very similar, you can actually write down the large A matrix model even at large n. And furthermore, this large n story can be applied to a variety of setups, including defect CFD, in which case like you have some D-brane in the bulk, and you consider like instead of sphere free energy, you take a disk free energy. And furthermore, in the large n context, the spectral curve, which you obtain the large A limit of this emergent matrix integral, actually has a nice holographic interpretation. And that's something I want to explain in the remaining 15 minutes. So to be concrete, let's consider some topological subsector defined on the BPS-Wilson line. So more concretely, I consider circular BPS-Wilson loop in n equals 4 super mils, and in particular, I take a fundamental Wilson loop, and which couples to a gauge field as well as to a scalar. And this was discussed by many authors, including Simone and Zeitlin and Royban. And this defines a nice 1D defect conformal field theory. And furthermore, there is a very nice topological subsector, which is in some sense a bit like a defect CFD analog of chiral algebra sector of n equals to superconformal field theory. So the topological subsector is defined by this. So you take a circular Wilson loop and then insert like a phi twiddle to L1. So what is phi twiddle? So phi twiddle is some linear combination of scalar field, which is like and this coefficient cosine theta and sine theta is correlated with the position of the insertion. And if you consider this kind of correlation functions, then you can actually show that these correlation functions do not depend on the distance between these operators. So it defines you the topological subsector. And furthermore, you can actually compute it using localization. And again, like technically, you need to use the Gram-Schmidt analysis again. And another thing I should emphasize is that unlike the extremal correlators discussed by Komargotsky, Tizzano, and Grassi, these topological sector have non-zero 3-point function or non-zero correlation function, even for non-extremal configurations, where the charges do not add up to 0. And okay, so and then so in this paper in 2018, we did the computation, and we realized that you can actually, for the case of 2-point function, you can actually get the large A matrix model. So this is the large A matrix model at large n that I was referring to. So it's a little bit more complicated because now instead of van der Monde, you get some like a weird generalization of the van der Monde factor. And so, but this is just like a result of like a localization computation. So let me just, but this matrix integral actually has an interesting historical like a development, because this expression was first derived from a completely different motivation by these authors using integrability analysis. And what we did in that paper was actually we just re-derived their result from localization and Gram-Schmidt analysis. However, like we didn't quite use it for the large charge expansion. And the only thing we and they did was to analyze large A limit and identify the spectral curve of this matrix model. And now, in order to connect this to the large charge story, we started looking at the large charge expansion of this matrix model. But before doing that, we also found some generalization of this large charge matrix model for the higher point function, because this is just 2-point function, but now like we can also insert several light operators. And actually, a generalization is quite simple. So in addition to what I just wrote in the previous slide, you just need to insert this quantity, where this Q is some polynomial of degree LK. And for example, Q1 is X, just given by X, and Q2 is just X squared plus dot, dot, dot. And from the matrix model point of view, this corresponds to insertion of some single trace operator in this matrix model. And then you can analyze like a large J5th limit of this matrix integral, and so which corresponds to J, like a size of the matrix to be large, and then taking G, coupling G to be large. And we need to take this limit because the potential term of the matrix model is given by this. And because G here is related to the 2-foot coupling in the n equals 4 supermaze in this way, that G going to infinity limit actually means strong coupling limit. And we also need to keep the ratio fixed. So this basically tells you that like the large J to 5th limit of this matrix model corresponds to the strong coupling limit of n equals 4 supermaze, in which the description in terms of ADS takes over. So let's talk about that, which is the holographic description. So the holographic description is quite, is well established. So as many people know that if you consider circular BPS boson loop in n equals 4 supermaze, then that is holographically due to the string worldsheet, which is hemisphere, which is anchored on this Wilson loop. And if you just do the conformal map, then you can also relate this configuration to this configuration. Here you have a global ADS, and here you have like a Wilson line, 2 Wilson lines in north pole and south pole of the sphere, and the string is stretching in between. So this is the description of the Wilson line without insertion. And one can also consider the Wilson line with insertions. And if you consider Wilson line with insertions, then this string becomes some like a non-trivial, gets some non-trivial profile and becomes excited string. But the solution is basically given by already known and given by these authors. And the explicit solution is given in terms of some elliptic functions. Now, so from this holographic point of view, actually the spectral curve of the matrix model that I was talking about earlier has a very nice simple interpretation. So let me explain what that is. So that if you consider string worldsheet on ADS5 times S5 background, it is known to be classically integrable, by which technically it means that all the classical solution of the string worldsheet can be classified by what's called spectral curve. Well, it has the same name. And the conserved charges, I'm not going to explain the details of the integrability, but this is the important point is that all the solutions can be classified by the curve, by some curve. And the conserved charges of those solutions, there are infinitely many of them because theory is integrable, corresponds to periods of the curve. And for this excited string, those people constructed, if you analyze the corresponding spectral curve of a string, which encodes all the conserved charges, then remarkably, you find that it coincides with the spectral curve of the large J matrix model that you defined from the localization, that you computed from the localization. And furthermore, what's nice about this is that on the string theory side, this same spectral curve actually controls correlation function beyond the topological subsectors, for example, all the non-BPS OPE data and anomalous dimensions. So let me just flash you the form of the spectral curve in this particular case. So the spectral curve has like a 2 branch cuts, and that is basically the reason why you get the elliptic curve when you try to express the solution. And in addition, there are infinitely many like special points in which px, the quantity px, which is often called the quasi momentum, take a integer times pi values. And by doing the computation, basically like a small, inserting some extra light fields on top of the classical string and then computing the correlation function, you discover that all these special points basically corresponds to some excitations on the large charge vacuums, some like excitation, non-trivial excitation on the large charge vacuum state, which you can see by OP decomposing, conformal block decomposition of the heavy light 4-point function in the heavy light channel. So this basically tells you that like this spectral curve, at least on the string theory side, controls all the non-BPS operators appearing in this heavy light OP decomposition. So this is a bit interesting because on the matrix model side or on the localization side, we got the spectral curve, but that was only for the BPS quantities because that's how you got the result. However, like the same spectral curve, that spectral curve coincides with the spectral curve coming from the holographic description of the string. And that spectral curve actually controls also the non-BPS quantities. So this leads to 2 questions to the audience. So one question is that maybe something similar is also true for this Grasik-Markovsky-Tizano story. So maybe one can ask, what is the physical interpretation of the large charge matrix model spectral curve derived in these papers, in this paper? And another question one can ask is that, does the spectral curve that they derived also control non-BPS quantity? So of course, like I don't know the answer, and maybe the answer might be no, but I just wanted to pose a question. Okay, so with this, let me just going to conclude. So today I basically talked about 3 topics. And the first topic was the large charge operator for higher rank superconformal field theory, in particular n equals 4 supermels. And I emphasized that the degeneracy makes like a story richer and more complicated. And I also said that if you take a particular operator, large charge operator, which is a single trace operator, then that's going to correspond to spherical D-brane, and that gives you the geometric realization of the large charge expansion. And the second topic I talked about is the double scaling limit, and I argue that it's governed by some centrally extended SU2/2 symmetry, which is the same symmetry as the one used by Bizert, but now in a completely different limit. And the third topic is about the large charge expansion on the Wilson line defect CFD. And I argue that you can also, in this case, you can derive emergent matrix model. And the spectral curve of the matrix model coincides with the spectral curve of the string, which is the holographic description of the same setup. And that also controls the non-BPS quantity. And so let me just end with the big open question. So far, I was mainly talking about like a large charge operator. In particular, in the first part, I was mainly talking about the large charge operator whose charge is like scale like n. And that is why the dual description was D-brane. But of course, like a big open question is what is the correct description for, or what is the kind of like a method to analyze the large charge operators whose charge scale like n square in the large n theory. And those typically correspond to something like a bubbling geometry or black holes. Okay, so let me end here.
So, wow. There must be, I expect there are many questions for the speaker. Well, while people are thinking about it, I certainly have a few. But yeah, I guess I was, maybe you got to it a little bit at the end, but I was going to ask in your analysis of the matrix model,
Mhm.
and the simplifications you found, I'm not sure if you explicitly said what was the assumption about the relationship between the size of J and N as you're taking both large.
Right, so, okay.
Maybe you said, but maybe I missed it.
Right, so this is about the last part. It's about the last part, right? So in the last part, actually, so yeah, indeed, like because I talked about different topics, I think it was a bit confusing. So in the last part, I actually took first n to infinity. So actually n was much larger than j.
Okay, I see. Okay, thank you. Yeah. Other questions?
Could you, probably I missed towards the end, could you explain again the relation you were arguing between the spectral curve and non-BPS operators?
Okay. Yes,
Right.
yeah. Indeed, I didn't explain the details of this. So, okay, so this is the spectral curve that you get from the string theory. And so, yeah, I was not giving the details, but in the string theory, and in particular, if you try to describe the string Warsh's theory using integrability, there is an important quantity called P of X, which is called Quasi Momentum. And for this particular solution, there are like two branch cuts. And at branch points, like we have Px of equals pi or Px equals minus pi. But on top of that, there are like infinitely many special points, which are in some sense like a degenerate branch cuts, which are defined by Px equals integer times pi. And at those points, you can also, okay, so the claim is that each of these points corresponds to like a different operators when you do the conformal block decomposition of heavy light in the heavy light channel. And you can actually express like a dimension of each operator in terms of like a quantities on the spectral curve evaluated at each point.
I see, thanks.
Are there any?
And that counts because your matrix model actually captures also higher point function, not only 2-point functions.
No. So this is an important point. So in the matrix model, actually, okay. So in the matrix model, it's a little bit hard to see. Well, there is no reason to. Well, you can still identify those points, but there is no reason to like expect that these points are special. Like the obviously like important points are these like a branch cut. And what I was saying is that the matrix model, from the matrix model point of view, it's completely unclear why these points are special and captures non-BPS excitations, because matrix model only captures BPS part. But it turns out that the spectral curve obtained from the matrix model coincides with the spectral curve obtained from the classical string. And the basically classical string on the ADS side knows about everything. And that's why these points are special and knows about non-BPS.
Okay, thanks.
Are there any further questions for the speaker? Well, in that case, let us thank Dr. Komatsu again for a really interesting talk.
Okay, thank you very much.
So I think our next speaker is Madalena Lemos. Whenever that's all set up.